I, I thought I would talk about some very simple topological aspects of fractional Hall effect. Um, so things like fractional charge, fractional statistics, and so on. So let me just remind you of where we are, and this would uh, also be a starting point for many of the calculations I will do, simple calculations. So first of all, I got some questions at the end of the talk in private, which I thought were very good questions. So others may also benefit from knowing answers to those questions. One was whether it's a non-perturbative phenomenon or a perturbative phenomenon. So what is it? Is fractional Hall effect a perturbative phenomenon? It's a non-perturbative phenomenon. I mean, there are several ways to see that. I guess the simplest way to see that is that no matter how small the interaction is, you can take Coulomb interaction, multiply it by a small number. It does not matter how small that number is, you will get fractional Hall effect. In fact, the spectrum would look exactly the same. I would just have to change the units on my y-axis, on the energy axis. So what we have done is, so we want to write down solutions for all states, all excitations, and so on. And rather than doing that one by one, we have constructed a mapping which is captured by this equation. So we have established a mapping between the interacting system at filling factor nu and a weakly interacting system at filling factor nu star. So I can actually put another label here. So I can list all of the states here. This label lists all possible states. So for example, if nu star is an integer, then the lowest energy state is the ground state. It's some integer number of filled lambda levels. Then I can create excited states and so on. So I list all of the states here in the order of increasing energy. And the postulate is that through this mapping, I can get all of the states at filling factor nu for interacting electrons in the same order in energy. So this factor, it attaches an even number of vortices to each electron. Okay, so what that means is if I have a factor like this, here Z sees one vortex at eta. Okay, because if I take Z around eta in a complete loop, the phase changes by 2 pi. If I have power 2p, that means Z sees 2p vortices at eta. And in this factor, each particle sees 2p vortices on every other particle. Okay, so in fact, part of the topology in fractional Hall effect comes from the fact that this vorticity cannot be changed continuously. It has to be an even number. You cannot add a vortex continuously or slowly. You either have it or you don't have it. So this object, which is the bound state of an electron and 2p vortices, is interpreted as a particle. It's called composite fermion. And we gave this intuitive picture, and I will give you another derivation today, which says that composite fermions experience an effective magnetic field, which is equal to B minus 2p rho phi naught. where rho is the density, phi naught is the flux quantum, and 2p is the vorticity of composite fermions. Now, we will assume in our lecture today that even without this lowest Landau level projection, this captures the qualitative physics correctly. Okay, so what the lowest Landau level projection does is it adjusts the energy scales a little bit. You know, if I'm doing a problem for fermions confined to the lowest Landau level, I should not have any kinetic energy. Things should depend only on the interaction energy. And this act does the job, but the physics is contained in this part. Okay, so we build in very good correlations. We attach vortices and so on. When we do the lowest Landau level projection, we are assuming that we are doing something perturbative, which fixes, which takes my wave function into the lowest Landau level, but does not destroy these nice correlations that we have built in. In fact, I can also write here another, so I can explicitly write what the lowest Landau level projection does, and this is one of the problems that we'll do later on. So, you know, about half an hour of this lecture would be a tutorial where some volunteers hopefully would stand up and work out some of the home assignment problems. But the explicit form of this lowest Landau level projection is so what this, so this is written not very precisely, but what I have to do here, this factor has z's and z bars. I first bring all the z bars to the left, and so in some sort of normal ordered form, then replace every z bar by this derivative. And I have to make sure that this derivative does not act on the Gaussian factor. Okay, so it only acts on the polynomial part. So this gives me precisely the lowest Landau level projected for. Okay, so last time there were lots of very nice questions, and if you were confused about the intuitive pathway that I gave you that took us to this equation, you have every right to be. It was just an intuitive argument. It was not a rigorous mathematical argument. But nonetheless, this statement is a precise statement that allows us to make lots of predictions and do calculations. And last time I already showed you comparisons with exact results and also experiments. Okay. I should make one more point. So we used this analogy to non-interacting fermions. What that means is that this wave function is the wave function of non-interacting fermions. But actually this whole thing is, it describes fully interacting electrons. So, you know, that can be seen from the fact that this wave function actually is very close to the actual eigenstate. But if you remember the spectra that we had, so let's say this is the ground state, and then there was particle hole pair. And remember that the actual energy of this particle hole pair excitation has a dispersion. And this dispersion comes because of the interaction between composite fermions. Otherwise, if the composite fermions were fully non-interacting, it would be flat. But you know, this wave function actually captures this entire dispersion very nicely. So this wave function actually goes much beyond, you know, the intuition that led to it initially. I should also say that another very nice thing that comes up in fractional Hall effect is that the length scale that governs the physics is actually H bar C over EB star. So that, as you go toward filling factor 1/2, as B star becomes smaller and smaller, this length scale can be much, much bigger than the magnetic length in the lowest lambda level. So this actually tells you what is the size of the quasi-particles of various fractional Hall states. The size is not given by the magnetic length. Okay, so one thing you may notice is that I have not said anything about fractional charge and fractional statistics. Okay, so one can actually understand the phenomenology of fractional Hall effect without saying those phrases. It's sufficient to know that there are composite fermions. They satisfy this property, and that gives you all of the fractional Hall effect. That gives you actually a microscopic theory that you can calculate with. Nonetheless, there are fractional charges in fractional statistics. So let's see how they come about. Right. Right. It is very surprising. So it's okay. So to an extent, you can understand it in the following way. Suppose I go to integer quantum Hall effect. Okay, I go to filling factor 1. I fill 1 lambda level. Now let's say I switch on the interaction between electrons. There will be some mixing with higher lambda levels, but because there is a gap, the wave function is going to be more or less very robust. It's not going to change too much from the wave function at filling factor 1. So similarly, the point is that, so of course in integer Hall effect, we have two distinct energies, the kinetic energy and the interaction energy. Here we have only one energy, but the point is, and that can be justified only a posteriori, that a large part of the interaction energy goes into the making of composite fermions and opening a gap. And that gives you this wave function. The residual interaction between composite fermions, which would give corrections to these wave functions, is small. Okay, so that's, so in other words, so there is a gap in fractional Hall effect. So residual interaction between composite fermions is in some sense small compared to the gap. The problem here is that both energy scales are set by the same Coulomb interaction. So it's a bit tricky. Okay. But let me just say, I think I made that yesterday also, that you can change the form of the interaction. So you can take a screened Coulomb, or you can take many different kinds of interactions, and it seems that the form of the wave function does not change too much. So the wave function is quite robust. It's not very sensitive to the actual form of the interaction. Okay, what was the second question? Right. Right. So we said that there are point flux quanta attached. So let's say we put the mod. Okay. The modulus here, if I put a modulus here, it would change the correlations, but it would not change the phase factors. We still have the property that if an electron goes around another electron, it sees 2p, OTC is bounded. Okay, but so what we have done is we wrote down that wave function, we noticed that it's not good. We have tried to do the best to modify the wave function without destroying the phase factors or without destroying this topological structure that is built into the wave function. Okay? So that step was completely ad hoc. So we have, so this wave function we don't know how to derive, but the motivation came from that sequence of steps that I described last time. Right. That's a very interesting question. So you see, the way to measure composite fermions is to measure this effective magnetic field. Okay? So composite fermions are topologically distinct from electrons. In this sense, electrons see the external magnetic field B, composite fermions see this magnetic field. And we'll see that that's a direct consequence of this binding of 2p vortices. Okay, we'll see that in a few minutes. But the point is, if you take a magnetometer, you bring it very close to the fractional Hall sample, it would always measure the external magnetic field. So you have to use composite fermions themselves to measure this effective magnetic field. And there are ways to do that. So yesterday I flashed some experiments. So one of them, for example, is let's say you have current flowing from here to here, and you measure voltage here. Okay? So so something is carrying current, this object goes in here, and then because of the magnetic field, it's going to bend. And it could either bend this way, or it could bend this way. So it could either go like this, or it could, be reflected and go like this. So whenever this object gets focused into this, you find that the voltage goes up. Okay, so you can measure the radius of this cyclotron orbit of whatever is carrying the current by this measure. And you find that the radius agrees with B star. So that's only one experiment, but there have been very, very clever, but you have to use composite fermions themselves to do the experiment. Okay. Any other questions? All right. So to derive things like fractional charge and fractional statistics, we basically need one calculation, which is the Berry phase of a vortex. So you all know Berry phase, but let me just write down the basic formula that I'm going to use. So the idea of Berry phase is you have a Hamiltonian, and let's say the Hamiltonian depends on some parameters. So this is not the coordinates. These are some external parameters. And so I have a parameter space, and what I'm going to do is start with a wave function and then go around in the parameter space, so execute a loop in the parameter space and ask what is the phase that the wave function acquires after a full loop. Let's first forget about time dependence. Let's solve the time independent problem. And let's say I have a solution which is phi r. So this is, you may say, this is the instantaneous solution. Let's say I know the solution for all r's. And furthermore, I don't want to, I want to do an adiabatic loop. So that means I will assume that there are no excitations nearby. Okay, so this state is separated from other states by a gap. Now, so let's say these are given. These are the instantaneous solutions. So I know just from the way the problem is set up that after so in this R space, could be a multidimensional space. When I come back to the same point, I have to end up with the same wave function apart from a phase. Okay, because we are not allowing any Zener tunneling. We are adiabatically going, following this ground state wave function all the time. So let's now write down the time dependent problem. So we say time dependence comes through time dependence in these parameters. So R here collectively denotes all the parameters. And the problem I need to solve So of the solution, which is that it should be it should have this. So at any given time, whatever value R has, it should be the instantaneous eigenstate of that. Then there is a phase coming just because the energy is changing as I'm going along this path. So I'm going to write exponential need more space. So this is what I would get just if the energy were just, this is the standard phase we get for some constant energy. But there would be an additional phase, which is called the Berry phase. Okay. So I will not do this, but I ask you to just substitute this thing in this equation, play with the various terms, and what you will discover is that gamma dot has this form. And in particular, if I ask, so this is true for any path, but now let's ask what happens if we go around one full loop, and that gives you the Berry phase, which is integral around that loop of So one of the nice properties of this, it's purely based on geometry. So it does not matter how slowly or fast we traverse the loop. Now, of course, we cannot go too fast, because if we go too fast, then we would have, we have to go sufficiently slowly to make sure that we are satisfying adiabaticity. But other than that, it depends only on the loop that we take in this parameter space. Okay, so, and in particular, and that's also one of the home assignment problems for you, you have heard of Arna-Bohm phase. Arna-Bohm phase is an example of Berry phase. Okay, so if you take a charged particle in the presence of a magnetic field, you move it around, you calculate this quantity, you find that it gives you precisely the Arna-Bohm phase. I should say that actually Berry phase, Arna-Bohm phase is more general, because Arna-Bohm phase is correct even without worrying about adiabaticity and so on. But certainly this would give you the Arna-Bohm phase. So let's now do the following calculation. And this was a calculation that was first done by Arovas, Schrieffer, and Wilczek. And Arovas has co-authored many other papers with Schrieffer in the field of fractional Hall effect. So what the calculation I'm going to do is the following. I will take some wave function and I'll create a vortex in it. And let's say I will even put some normalization constant, and I will call that wave function psi eta. So eta tells me where the vortex is. Okay? So again, you remember vortex has the property that any particle going around eta will produce a phase of 2 pi. And this actually creates a hole in that region because I know that there is no particle at the position eta. So if I put any z equal to eta, I get 0. So the calculation I will do is I will take eta in a circular loop and ask what's the Berry phase produced by that. Okay? In fact, so I'm going to calculate eta, but maybe one can already guess the answer. Can you guess the answer? So let me ask a leading question. If I take eta, so we said if I take z around eta, what does that give us? What phase would that give us? 2 pi. If I take eta around z, what will that give me? 2 pi. So if I am taking eta around this loop, what phase is it going to give me? Exactly. It's going to be equal to the number of particles. So let's say n enclosed times 2 pi. Each particle inside is going to give me a phase of 2 pi. Okay, but let me nonetheless do the calculation because it's kind of a nice little calculation. This is the answer we are going to get. So here I will do okay, that's a Berry phase. So I have to take derivative with respect to eta. If I take derivative with respect to eta, let me see if I can write this like this. Can you all see this? So when I take derivative with respect to eta, I have a product of terms here. So derivative acts on the first term or the second term. I get a sum of terms. It acts on the first term or the second term or the third term. Gives me a minus sign. So what I have done is I have then factored out this full factor and the sum that reduces to this. Okay? Then I'm going to do something. I'm going to do the following. So this may seem kind of a bit complicated, but I'm going to introduce the density operator and rewrite this thing in the following way. where this density operator is okay. So you substitute this here, you do the integral, you will recover the previous equation. All right. Now we are going to switch the order of integration, and we realize that we can do the eta integral. That's the simplest contour integral you can do. So when we do the eta integral, we get either 0 or some constant. We get 0 if z is outside this loop, and we get 2 pi, or we get 2 pi when z is inside the loop. So the answer is that this is equal to integral d squared r, where r is less than do not confuse with this capital R with this capital R here. Okay, this was just a collective symbol for all parameters. Here, this capital R is the radius. So long as R is less than this capital R, I will get 2 pi times the density. Okay, and this is precisely 2 pi times the number of particles enclosed. Okay, so this will be the result that I'm going to use to derive things like fractional charge, fractional statistics, and so on. And to begin with, let me derive the formula for the effective magnetic field. So what I'm going to do is, how do I know what magnetic field composite fermions are saying? I take a composite fermion in a closed loop and ask what is the Berry phase associated with it. So, take the Berry phase. So what is a composite fermion? It's an electron and 2p vortices. Okay, when I'm taking a composite fermion in a closed loop, I'm taking an electron and 2p vortices in that closed loop. When I take an electron in a loop, it just gives me the Arnold-Bohm phase. So that is this is closed loop of area A. Okay, and the sign you have to work out, but for electron, for a magnetic field which is pointing in the positive z direction, you get a minus sign here. Okay, then we have 2 pi, 2p, and enclosed. Right? So that's the answer, because each of the vortices gives me a phase of 2 pi times n enclosed. We have 2p vortices, so that's the answer. Now I'm going to make a mean field approximation, and I'm going to say that I will write this as density times the area. So I will replace n enclosed by its average value, and that gives me minus 2 pi A divided by phi naught. Okay, in fact, I can skip that step. So let me say that I'm going to interpret that as the Arna-Bohm phase coming from an effective magnetic field B star. And you can see that this equation is the same as the equation here for B star. So what is happening is that when a composite fermion is moving around, there is of course an Arna-Bohm phase, but there are also phases coming from vortices bound to other particles. And the phases due to vortices on other particles, they cancel the Arna-Bohm phase to some extent. And this can be interpreted in terms of an Arna-Bohm phase in an effective magnetic field. Okay. So let's come to fractional charge. So the question is, so let's calculate the fractional charge for this vortex. And from here, we will go to the fractional charge of some more elementary objects. A vortex, so first of all, what is the meaning of the charge? How do I define the charge here? How would I define the charge of a vortex? Yeah, you have done the calculation. I'm just asking just conceptually what's the meaning of the charge of a vortex? Yeah. That's good. So you see, if I did not have this, I have some state and let's say it's uniform. When I multiply by this, I know that electrons are repelled away from the position eta, and therefore how much of the charge is moved away, that's the charge of a vortex. So in other words, if psi naught has the density profile like this, and putting a vortex at eta, and let's say this is eta, it changes the density profile to that. There is some missing charge, so I can integrate this difference, and that's a charge of a vortex. So there are several ways to get the charge of a vortex. One way is just to say that I'm going to interpret this result in terms of, so let's say the vortex has charge E sub V. Then I can interpret this in terms of the Arna-Bohm phase of a particle of charge E sub V. So here I say this is equal to BA divided by HC divided by E sub V. Okay? So let's work with this a little bit. So the filling factor, I want to write this answer in terms of filling factor. The filling factor is defined as the number of, remember filling factor was density divided by B phi naught. Okay, that's the definition of the filling factor. Density is N enclosed divided by the area times rho So let's see, am I missing something? I'm missing a. Okay, I believe that's correct. So if you compare, okay, let's substitute for B from that equation. You combine these two equations, and from this you will find that the charge of a vortex is filling factor measured in units of the electron charge. Okay. It actually makes sense because when I create a vortex, what I'm doing is I'm emptying precisely one orbital. And the charge in each orbital is exactly equal to the filling factor. And therefore, the charge of a vortex is equal to the filling factor measured in units of the electron charge. Another way to see the charge of a vortex is to do this thought experiments that we talked about last time. So I had mentioned in the context of Laflin's wave function. So if I take a disk, I pierce the disk. So I create a hole, a point hole in the disk, and I put a magnetic solenoid, and I slowly insert one flux quantum. Okay? So I have come back to the same Hamiltonian as before, but everything has moved out a little bit. So the question is how much charge has moved out. So that's also the charge of a vortex. So to do that calculation, again, that's something that can be done quickly. Let me consider a circle far away and ask how much charge has moved out of the circle. Okay, as I change flux from 0 to 1 unit. And this is a calculation that Jaideep had also mentioned. Okay, but let me just do it, just fill in all the steps. So the charge that has moved out so let's say this radius of this circle is r. So this loop is the loop, the circumference is 2 pi r. If Jr is the current density, I integrate over time. That gives me the total charge. What is Jr? So I'm assuming that there is no disorder. It's an incompressible state. So J is equal to sigma E, which are all in perpendicular directions to each other. So the current in the radial direction depends on the electric field in the azimuthal direction, and the coefficient that describes this proportionality is just the Hall conductance. So we have this. Now what is E phi? E phi is being produced. Where do I get an azimuthal electric field? From the fact that we are changing this flux. Okay, there is a time dependence, so that just Faraday's law. So E phi is equal to minus 1 over 2 pi r, and I think there is a factor of 1 over c, d phi dt. So you put this for E phi, and for Hall conductance, you so for Hall conductance, I say it's nu E squared over h. So nu is some fraction like 2/5 or one of these incompressible fractions. You substitute all of this, and you will find that this result becomes equal to sigma h 1 over c integral integral d phi, and there may be a minus sign here. Phi goes from 0 to phi naught, and so I should clarify, I have taken this loop far away that the Hall conductivity is constant. You know, very close to this place where I'm piercing the flux, the density itself is not constant, so the Hall conductivity is not, it has some dependence on the position, but far away it has no dependence and it's given by this formula. So I substitute for sigma h, I have nu E squared over h, I have phi naught, this gives phi naught, so that's hc over E, and this gives you, okay, so this amount of charge goes out, and therefore the charge of the quasi-hole is some positive charge that's given precisely by nu. Okay, so we can already see that there are objects in fractional Hall effect which have fractional charge. But what is the elementary charge? That's a question we should ask. So the picture we have in mind is the following. So suppose I go to some filling factor n over 2pn plus 1. What does the ground state look like? So I have n of these lambda levels of composite fermions which are full. And then there are empty lambda levels of composite fermions. Now I'm going to add one extra composite fermion here, and I'm going to ask what's the charge of this object. Okay. So what does that mean? I add an electron, but this electron will capture 2p vortices to turn into a composite fermion, and we want the charge of that full object. So it's trivial. So the charge of this object is equal to the charge of an electron, which is -1. Okay, let me measure it in units of electric charge. So charge of an electron is -1. The charge of one vortex is n over 2pn plus 1, but I have 2p vortices, and they all have positive charges. Okay, so this is an electron plus charge of 2p vortices, and that gives me -1 over 2pn plus 1. So that's the fractional charge of a composite fermion. One can actually get it in a different way. So let's say, let's take this to be the state at filling factor n over 2pn plus 1. Okay, so that's the ground state at this filling factor. And let me create a vortex. To simplify things, let's create a vortex at origin. So okay. So the question is, how many elementary holes are created through this? So remember, yesterday we did this problem in which we found that if I create a hole in one filled lambda level, it pulls out a factor of Zi, product over I. Remember that calculation? So now I'm asking, so if I write a wave function of this type, that's effectively, it empties the state with z to the 0 because it converts this row into, it increases the angular momentum of every particle by 1 unit. So I'm left with the hole in angular momentum 0 state. Now let's say, so this is one filled lambda level. If I have two filled lambda levels and I multiply by this factor, what do I get? So if my filling factor is 2, what is the charge of this object? What is the charge of a vortex? We already calculated this. If the filling factor is 2, what's the charge? 2. The charge is 2. If the filling factor is 3, charge is 3. Because, and this is something you should be able to figure out in a minute, it creates a hole in each of the lambda levels. Okay. So what is happening here, if I consider this object, then this is creating, so I'm going this way, this is creating a hole in each one of them. I know that the total charge of this is n over 2pn plus 1, but there are n of these, and I can move them around. In this vortex, they just happen to be at the same place, but they have their own independent existence. So there's n of them, and therefore to get the charge of a single one of them, I have to divide by n, and that would give me the same charge, but for a hole. Of course, we know that hole must have the same charge, same magnitude. Right? We know that because I can excite a particle from here to here. Overall, this gives me no additional charge. If the charge of this is minus this amount, then the charge of this has to be plus the same amount. So the magnitude of the charges of these two excitations must be the same. Okay, so that brings us to fractional statistics, and you'll see that a one-step calculation will give us the fractional statistics for all fractions. And the calculation is, it goes as follows. Okay, so first of all, let me define fractional statistics. So fractional statistics is a generalization of the idea of bosons and fermions. And one way to define it is to say that suppose I have some particles which satisfy the property that if I take one particle around another, this loop acquires a phase of e to the power I 2 pi alpha, where alpha is called the statistical angle. And the crucial thing is that this phase should not depend on the shape or the size of the loop. It only cares about whether you have gone around this particle or not. On the other hand, if you take some other loop, you get e to the 0. You get no phase. So let's say if we had some particles of this type, they are said to be anyas. They are said to obey fractional statistics. Okay, so if alpha is 0, these are bosons. If alpha is 1, okay, if alpha is an even integer, these are bosons. And I'm saying that because one full loop around is equivalent to 2 exchanges. Okay, because half a loop is like an exchange because I can take it around half a loop and then do a rigid translation. So that's like an exchange of 2 particles, and a full loop is like two exchanges. So half a loop gives a phase of e to the power I pi alpha. So if alpha is an odd integer, that's -1, that's fermions. If alpha is an even integer, then I have boson. And if alpha takes some arbitrary value, then these are called particles with fractional statistics or anyons. Okay, so that's the definition of fractional statistics. It should be, so I will say that one can define fractional statistics only in 2 dimensions. Why is that? Excellent. So the thing is that I should not be able to continuously deform this loop into this loop. Okay. So in fact, strictly speaking, I should imagine that space has punctures at the positions of all the particles. So which means there is a hardcore condition, infinite repulsion. But I should not be able to deform this loop through this. That I can do in 2 dimensions by changing the topology by puncturing the space at all particle positions. But in 3 dimensions, I can, of course, lift the loop out of the plane of the blackboard and deform it into the other loop. So there is no topological distinction between this loop and that. So one can define it only in 2 dimensions. So let's see how we get particles with fractional statistics here. In fact, let's calculate the fractional statistics. So the idea is very simple. I'm going to now imagine a situation where I have a fractional Hall state. On top of that, I'm going to put 2 particles. Okay, so these are particles which are composite fermions, electrons plus vortices. They have fractional charge relative to the uniform background state. And I'm going to ask what happens when I take one particle around the other. Now there is a slight complication here, which is that even when I do not have the other particle, let's say I take this particle around in a loop, even when I don't have the other particle, there is some Berry phase. Okay, in fact, we calculated the Berry phase here. It's this Berry phase. Okay, so how do we define fractional statistics? We are going to say that I'm going to do 2 calculations. One in which I take this particle around in a loop without any other particle. Then I insert another particle somewhere, do the same calculation, and ask how much the Berry phase changes by. Okay, so that change will be attributed to the statistical phase angle. So I'm going to just do the calculation from here. So I'm going to calculate change in the Berry phase, delta of gamma. Does this change between the 2 loops? Does this change? Why does this change? Exactly. The number of enclosed particles has changed by, it's not changed by 1. So when I add a composite fermion, I have changed the number of electrons by a fraction. Okay, so the answer is delta gamma is equal to 2 pi 2p n enclosed and again I'm going to calculate the change in the average number of particles. So that's equal to 2 pi 2p and the number of n enclosed is minus, well, let's not worry about the sign. It's 1 over 2pn plus 1. So that gives me the phase angle. Okay, so a 1-line calculation gives us the value of fractional statistics for all fractional Hall states. Essentially what happens is I mean, it's actually a product of the vorticity times the charge. Okay. So, right. Let me quickly, I'm going slower than I had expected. Let me quickly introduce some very basic ideas on Chern-Simons field theory. Very, just introduce how one goes about Chern-Simons field theory. And then point out some open problems in the field. So the Hamiltonian version. So before I go to the Lagrangian, I will just write it down, but let's start with the Hamiltonian. And this is something, I had done some version of this in my lecture yesterday. So we have the kinetic energy part. So that's the Coulomb interaction between the particles. This is kinetic energy. Now, in principle, if we go to the lowest lambda level, we don't have this term anymore. It's just constant. But it turns out that to do Chern-Simons theory, one has to keep it, at least initially. In fact, one does not know how to get rid of it completely. So this is our Schrodinger's equation, and we are going to make a singular gauge transformation, which is defined by this formula here. So in terms of the Schrodinger's equation for this Chern-Simons wave function, so this is psi Cs. Cs stands for Chern-Simons. The Hamiltonian looks like this. So maybe I can say HCS. And this vector potential is the same vector potential that I had written down yesterday. For completeness, let me write it once again. And this has the property that del cross A is equal to 2p phi naught times the density. So density means at the position, so this is the density operator, it's sum over I. Okay, so far this is exact. I mean, there may be some subtleties associated with the singularity of the gauge transformation, but anyway, it's basically exact. Now, what do we do here? So we have done something that is kind of reverse of what we had done yesterday. So we have started out with a problem with the full magnetic field. And this vector potential, notice it has a minus sign. So it's attaching 2p flux quanta in the direction opposite to the external magnetic field. But if you take the average magnetic field, so if you count the flux quanta bound to the particles also as being part of the external magnetic field, then you get the same effective magnetic field that we had yesterday. So what one does here, the way one proceeds, I mean, so far it's exact, but beyond this, there's nothing exact one can do. So one has to make some approximation, and the approximation is this mean field theory that I had mentioned yesterday. So one writes A minus A as some vector, some uniform part plus some part which is fluctuations, and then one can write this as 1 over 2 MB So what I have done is I substitute that here. Then I collect all of the terms which are proportional to fluctuations delta A, and I call that V prime. So the Hamiltonian looks like this. And then the idea is that you start with the solutions here, and you treat this perturbatively. So we know that Coulomb interaction by itself is non-perturbative. We know that V primed by itself is non-perturbative. The hope is that the combination of these two can be treated perturbatively, which means that the non-perturbative physics is hopefully built into this step. That's the assumption. Exactly. A star gives the uniform magnetic field, which is equal to B star. Okay, so that's roughly the basic idea of writing a field theory. One can actually write this in the Chern-Simons language. So if you write the Lagrangian, it has the standard form. And this constraint that del cross little a is essentially equal to the density is imposed by adding a term here. So if you look at this term and this term, A naught is like a Lagrange multiplier. So it just gives you a constraint, which means that the coefficient of A naught must be equal to 0, and that's precisely this constraint. So one imposes the nature of this through this term, and this is, some of you may recognize, this is like the Chern-Simons term. Okay, so if you write the full Chern-Simons term, which has the form then in the Coulomb gauge it reduces to this. But anyway, I don't want to go too much into that. So basically, let me spend the last few minutes in just pointing out what is remaining. So are there any questions so far? Right, right, right. That's correct. That's right. So in fact, this corresponds quite closely to this, where the Berry phase coming from the vortices, they cancel part of the effect of part of the external field. Okay. So if you calculate the Berry phases coming from the vortices, each vortex produces a Berry phase that corresponds to one flux quantum pointing in the negative direction. So that's what is done here. Now, to say that one can write this and do a perturbation theory, that just, I mean, there is no rigorous justification. There is no small parameter in the problem. So neither this nor this is small. So it's justified by the fact that we know that at some level we know that this picture of free particles in an effective magnetic field does explain experiments. So that is the justification for writing the theory in this fashion. Yeah, I mean, a gauge transformation is only, it can only produce phases. Okay, so if you want to do a gauge transformation, you are kind of stuck with this. We do not know. I mean, one would love to see how to do things without introducing this denominator, but one does not know. All right. Any other questions? Yeah. 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 So, okay, can somebody else help me with this? Can somebody else answer this? What was the motivation of attaching an even number of flux quanta to electrons? Why attach flux quanta at all? Right. That's right. So okay, so it's not a proof, it's just motivation. So we do not know what to do with electrons when they are in this high magnetic field at some fractional filling. This is a way by which we can map this problem into a problem of particles in a much smaller magnetic field. And then one finds, lo and behold, that whenever the filling factor in this reduced magnetic field is an integer, that actually corresponds to the observed fractional velocity. So some of the justification is a posteriori, but basically the idea was, so it's like in superconductivity. Let's say you want to understand why the resistance is 0, and you know about Bose superfluidity. So you say, okay, there must be some sort of bosons here. And then you ask what these bosons could be. I mean, there could be 2 electrons or there could be 4 electrons. And then you have to worry about what is the wave function of these bosons. Here, it's more complicated. because composite fermions, in some sense, a vortex is made up of all particles. So it's a much more complicated bound state. I have an electron and vortices, but a vortex itself involves everything else. So it's more complicated, but it's essentially a way to map the fractional Hall problem into integer Hall. So nobody knew that this would actually work, okay, but that was the motivation. Any other question? Okay, so let me just make a few points. Which problem is that? Right. Right. So in XY model, you can write the problem either in terms of particles or vortices. Okay. You can do either in terms of spin with these. So yeah. So I think it's not the first time when one thinks of a vortex as a particle. So that already occurs. That's in fact important for costless Thouless transition. And even there, the vortices are topological in the same sense as they are here. But I don't know. This idea that you can, I suspect that even there, perhaps the vortices produce some sort of effective magnetic field. Although is that true? But there, the number of vortices and anti-vortices is equal. So therefore, on the whole, the magnetic field cancels. Anything else? Okay, so let me just say that, let me make one last point before I go to, open problems are, I will just mention what they are, but one of the open problems is that I think there is some structure here that is yet to be discovered. Okay, some mathematical structure, and I certainly don't have the neurons in my brain to discover that mathematical structure. But another open problem is if you go to second lambda level. So all the physics I described to you works in n equals 0 lambda level. If you go to the n equals 1 lambda level, at first blush you would think it should be the same. So the Hilbert space for both lambda levels is identical. The only thing that changes is the matrix elements, but still you have repulsive interaction. So you would think, okay, it should behave similarly, but it turns out that second lambda level is different from the lowest lambda level. Many of the states, so the fractions that are seen in the second lambda level, so first of all, I begin with 2 plus something, 2 because I fill the lowest lambda level with both spins. Okay, so experimentally, I have 2 plus 1/3, 2 plus 2/5. So they seem to be the same fractions that we see in the lowest lambda level. But even 1/3 is very hard to understand. 2/5, I think it's fairly clear now that this 2/5 is different from the 2/5 that corresponds to 2 filled lambda levels of composite fermions. The most surprising thing perhaps is 1/2. So remember at filling factor 1/2 in the lowest lambda level, there is a Fermi. There is no fractional Hall effect. It turns out that at 2 plus 1/2, which is the 5/2 state, there is a fractional Hall effect. And so this puzzle actually existed before composite fermion theory. And then now it is believed that this state is actually a P-wave superconductor of composite fermions. So the composite fermions form a Fermi, but there is an effective interaction between them which is weakly attractive. Okay, so I told you composite fermions have very weak interaction, but sometimes the interaction can be attractive. And at 2 + 1/2, we have composite fermions with weakly attractive interaction, and it's believed that because of pairing, a gap opens up to produce fractional Hall effect. So what happens is, you can think of binding of vortices as creating a correlation hole around each electron. Okay, so it's like screening in some sense. But the screening is quantized, see, because the vorticity is quantized, and therefore sometimes screening can overshoot a little, it can overscreen, and that's what it seems to be at 5/2. So one can do the following calculation, which we did. Let's say I create a Fermi sea of composite fermions. I do the Cooper problem. So I put 2 particles on top of this Fermi sea of composite fermions, and then ask what is the interaction between those 2 particles. And we find that in the lowest lambda level, at 1/2, the interaction is repulsive. At 5/2, it's attractive. It's all coming from the interaction between electrons, but the interaction between electrons in the second lambda level is a bit less repulsive than the interaction between electrons in the lowest lambda level. And once you attach vortices, it kind of becomes attractive. So it's an interesting example where one can get something like superconductivity in a model that was purely repulsive to begin with. You say, how can that happen? That's because the objects that do the pairing are not electrons, but they are composite fermions. Yeah. Right. No, you forget about the filled lambda level. So the interaction between composite fermions has to be calculated. It's some sort of, depends on the interaction between electrons, but it has to be calculated. So since we know how to write wave functions, I can just write this wave function and calculate how the interaction depends as a function of the distance. Yeah. Yeah.
Will it be attractive or repulsive?
So it turns out that if you go to, let's say, 4 + 1/2, we want to go to third lambda level, there it turns out that composite fermions are not relevant. There is no fractional Hall effect. You get the simplest solution, stripes. Okay, so there you see stripes, and even higher lambda levels you see stripes. So in the lowest lambda level, you get beautifully everything matches with composite fermions. In very high lambda levels, everything matches with mean field theory for electrons. Okay, stripes. In n = 1, the second lambda level, it's kind of not sure which way to go. So it's very close to instability. Okay. You make charge density. Yeah, you do charge density waves. No, you keep things in a given lambda level. So what is found, let's say you go to filling factor 7. Okay, 7 + 1/2. Then what you would find is that there will be stripes where it goes between 7/8, 7/8. Because it turns out that by filling lambda levels completely, there is some exchange type energy to be gained, so the system chooses this kind of stripe phase. Or you could get Wigner crystal type phases. You get these other kind of phases that you can describe in terms of electrons. These are also correlated, but in a simpler way.
Is there any way to understand why P wave is the natural instability for this 5/2 state?
Okay, if the system is fully spin polarized, then that's the only instability. That's a simple. No, as opposed to S wave or S wave is not possible. So there is a wave function that one writes, which is called the Pfaffian wave function. So this is the wave function for filling factor 5/2, but I'm writing 1/2 because I'm writing this wave function only for the electrons in the n equals 1 lambda level. This has the form Pfaffian of 1 over Zi minus Zj times the Gaussian factor. The Pfaffian, the definition of Pfaffian of an antisymmetric matrix is defined in the following fashion. Okay, that's the definition of the Pfaffian, where A denotes antisymmetrization. Okay, so you might notice that this is nothing but the BCS wave function. So BCS wave function would be written as okay. So this is the pair wave function, and this describes a P wave pair because its phases are e to the power I theta 1, 2. So to the extent that this wave function is correct, and there is there's numerical evidence. So numerics have shown two things. One is that even if you reduce the Zeeman energy very small, the ground state at this filling factor is fully spin polarized. That's number one. Number two, they have shown that there is a decent overlap between this wave function and the exact wave function. So overlap is around 70, 80%. So it's not completely conclusive, but it's certainly okay. So to the extent that this wave function is correct, it's P wave. That's the most natural wave function one can write. In fact, I should say that this wave function was responsible for reintroducing the phrase Majorana fermions into modern condensed matter physics, because the vortices of this, they have a Majorana sitting at the center. These Majoranas are actually half of a composite fermion. So it's a sum of composite fermion creation plus annihilation operators. And there's been a lot of experiments trying to see those Majoranas, but not successful. I mean, sometimes they're tantalizing close, but it's not conclusive yet. No, it's fully gapped. It's Px plus IPy. Yeah, 2 minus 1/2 is 1/2 in the lowest lambda level of holes. So at least in the limit that I can ignore higher lambda levels, it's identical to 1/2. So 1/2 and 3/2 are the same, they're related by particle velocity. Okay, so if you fill one spin component completely, then it's the other spin component making filling factor 1/2. So similarly, 5/2 and 7/2 are the same. Fractional Hall effect has been seen at both of them. What is magnetic impurity going to do? I mean, spin is fully polarized. Yeah. Yeah, so one way to kill it is by raising the temperature. Okay, so what they have found is that if they raise the temperature and kill it, they see that the permanency of composite fermions comes up. So there are some signatures experimentally of permissive composite. But there is no sharp transition. So this is not a superconductor. Okay, it's not a superconductor of electrons. It's a superconductor of composite fermions, you may say. So what happens is that it's the same, but what happens is that uh, if you take so there is a way to translate the quantities of composite fermions, let's say within Chern-Simons theory, to quantities of electrons. And a superconductor here would give you an incompressible state. So the resistance is not zero, it's exponentially small. So as far as, I mean, it's experimentally, there is no proof that there is pairing of, there is any sort of pairing in this state. So that's, I mean, it looks just like any other fractional Hall state experiment, except that it has an even denominator. Any other questions? So I think since we are already out of time, we will not do the problems. Those of you who worked the problems out and were ready to volunteer, I would like to thank you. But thanks to everyone for listening.
Questions?
You do random phase approximation. So yeah, so there is a way to translate these quantities into measurable quantities for electrons. So whatever one is calculating, okay, so once we do one has to do a mean field approximation, okay? So in the transform language, you do all the calculations, but then you have to transform back to the electron language, and there is a dictionary to convert all the resistances, resistivities, etc., into the resistivities that would be measured experimentally. Yeah. Yeah. Yeah, yeah. So in fact, that goes back to the question of things like effective mass. So if you say that composite fermions have an effective mass, and let me say along one sequence or composite fermions carrying two flux quanta, they all have the same effective mass. Then the gap would be proportional to the effective magnetic field, and therefore, as you go closer to 1/2, the effective magnetic field is becoming smaller and smaller. So one can see already that the scaling of the gap should be that the states become progressively weaker, because the strength of a state is dependent upon the gap to excitation. One can actually do a little more. So one can show that the scaling that one gets from this very simple picture actually works pretty well against the calculated gaps. The width of the plateaus also works out, because the plateau for, let's say, filling factor 1/3, or let's say 2/5, okay, it extends because nu equals 2/5 maps into nu star equals 2. So this plateau will go from nu star from 1.5 to 2.5. So one can, in the ideal situation, that would be the width. So when composite fermion filling is an integer plus 1/2, that's where transition to the next plateau would take place. And that also agrees quite well with it. I mean, you have to convert this into nu, so I think this would give you, anyway, whatever filling factor this gives. Yeah, so they are separated in magnetic field. So the sequence where we have composite fermions carrying 2 flux quanta, that goes from 1/3 to 2/3. Then 1/3 to 1/5, you have composite fermions carrying 4 flux quanta and so on. And then there are these weaker states. I'm ignoring those for this question. Right. Yeah. So, see the interesting, so let's take the analogy of a superconductor. So typically we say ground state has Cooper pairs, but to create excitations, you have to break Cooper pairs. Here, what happens is that suppose I am at filling factor 2/5 again, that's 2 filled lambda levels of composite fermions. To create excitation, I excite a composite fermion in full integrity to the third composite fermion lambda level. And at least for the first few bands, which are well defined in numerical calculations, we find that this continues to work. So we can define things in terms of composite fermions. But at the same time, I know that if I go to very extremely excited states, it has to be just electrons. Because all these correlations have to go away for very high energy excited states. It's an intuitive statement. So very high energy excited states correspond to very high temperatures. Eventually, these correlations have to go. But there is no very good understanding of how that happens. Fortunately, knowing just the low energy physics is good enough for explaining lots of experiments.
No question?
Okay.
On wave function is in the right class in some sense, but if one computes the overlap with an exact solution for a sufficiently large system, the overlap should go to 0, something like that, he said.
Right. So that's true, but it's a meaningless statement for the following reason. Suppose I want to write wave function for a Bose condensate. Okay, so I will write a wave function. I will put all bosons in the same state. And I know this describes the physics correctly. Okay, but let's say I'm making a tiny error in the wave function of each single boson. Then if I calculate the overlap between wave functions, I know that the overlap between this and the exact will go down exponentially, where e to the power minus epsilon is the overlap between each single particle wave function. So I guess the point I'm making is that for composite fermions, there are many things which are independent of the wave function, which is the structure of the low energy states, counting of the low energy states, where we have incompressibility and so on. Plus the overlaps are so good that any quantity that you calculate with it, let's say pair correlation function or the gaps, they would come out extremely accurately, even in the thermodynamic. So the fact that the overlap goes to 0 is like making a sow's ear out of a silk purse, I would say. So the overlaps are so large, but saying that, so that tells you that exactly. And the epsilon is extremely small for composite, for these waves. Okay. So the fact that overlaps will go to 0, that's obviously true. there's no wave function which will have overlap equal to 1 with any real wave function. But that does not mean that there is anything wrong with the wave. I mean, so the right, okay, so from some perspective, the more important thing is to have the correct physics, but you would also like to have it as good quantitatively as possible. Because eventually correct physics has to be borne out by good numbers. Yeah. So the thing is that you calculate gaps using these wave functions and you put them against experiments, and that's so you want to get the numbers right too. Yeah. So log of the overlap divided by n, that's this epsilon. That's a sensible thing to do. Yeah. So the energy per particle would be extremely close to the energy per particle of the exact wave function. Right. Right. It's one of those things and I would love to know the answer to that. We do not know how to write these wave functions on torus. We know how to write them in the disk geometry. Somehow we know how to write them in the spherical geometry, but with more complicated genuses, we don't really know. So I have spent a lot of time in trying to figure out how to write the wave function in the torus geometry. Let me also tell you why that's the case, in case somebody here wants to think about it. See, in the disk geometry, it's a neat thing that if I take a lowest lambda level wave function, or if I take two lambda level wave functions and multiply them, I get a legitimate lambda level wave. In the spherical geometry, again, that's true. I mean, you get a legitimate lambda level wave function at a different magnetic field, but you get something. In the torus geometry, that's not the case. And there have been some ideas. I mean, there is at least one paper in the literature which claims to write down these wave functions in the torus geometry, but they were not able to do anything beyond writing it down, and I have not. I mean, it's certainly not a very neat way to write these wave functions. So that, I think, would be very useful. And they should be well-defined wave functions. So ideally, what one would like to do is, I mean, so this wave function can be written as phi 1 to the power 2p phi n, okay, where this is wave function of n field lambda levels. This is wave function of 1 field lambda level. That's like this. So one can build it this way. It's products of lambda level wave function. So in these geometries, the product turns out to be a valid wave function. We have to project it and so on, but it's a valid wave function to begin with. In the torus geometry, it doesn't work. I have spent a lot of time but failed to write it. If one could write them, then of course they have to give the correct degeneracies.